Good day, ladies and gentlemen. Today, hopefully this is a short video about the logistic differential equation and how to graph the population model, the logistic growth model from the differential equation given the initial condition. And then we're going to end the video with how to actually find the growth model by using the formulas that were given in the previous video. So the first thing we're going to need to realize is we're going to need to be able to, and looking at the graph of this population model given this is going to be pretty dick and dog easy. So all I'm going to do is realize that the maximum carrying capacity here, and we all should recognize what that is going to be 1200. And that's going to be what we're going to call horizontal asymptote of the population model. The other thing we know is this guy right here. At time t equals 0, the population is starting off at 20. So we're going to use those two informations. And what else do we know? What else do we know about this differential equation is that with respect to the growth model, we had a video about that, we're going to have another video on this, is that the growth model has a point of inflection at 1/2 the maximum carrying capacity. So we're going to have this inflection point at when the population is equal to 600. So those are the three things really that we need to know to graph the population model. So I'm going to come down here and extend this page so I can come back to it. I'm going to extend this page. I'm going to create a little, make sure I'm on a black line. I am. Okay. And I need to realize that these values here are going to be my time. And this is going to be my population right here. This is the population growth. Okay, so what do I need to realize? I need to realize that at t equals 0, the population is 20. So we can just put any point down here. This point right here is going to be 0, 20, because I'm looking at the population as a function of time. The other thing I need to do, all I need to do then, is to sketch this horizontal asymptote, this carrying capacity right here. And so I'm going to create a horizontal asymptote with my line tool that's going to be equal to where the population is 1200. So I'm going to come here, I'm going to turn my line tool to yellow. I'm just simply going to come down here and create, whoa, that's almost like freaky. And create a, okay, so that I'm going to let that be the population of 1200. That's where the population is equal to 1200. That guy right there. And then if I go half of that, and I'll do a light green line this time, if I do 1/2 of that, and make sure that it's just 1/2. 1/2 of 1200 is going to be 600. Now let's move this guy up here out of the way again. I'm not sure if you can see the record button. I really don't. 600. And that's where the inflection point of this graph is going to take place. So here I go. I'm just going to sketch the graph. It's going to max out at 1200. It's going to come down here. And at this point right here, it's going to change from concave down to concave up. Concave up. I'm going to get rid of this little thing right here. It's bothering me. Okay. And that's really all there is to do. All there is to graphing this model, and it may be, I might be able to do a better sketch of it, because it is going to increase pretty quick as it goes. There you go. That's a better That's a better graph. And keep in mind, this is the graph of the population as a function of time. This right here, what we started with, this right here, this is the derivative of this particular guy. Okay, and I think this next slide, all I've done is, yes, so all I've done is reiterate what I've done on that previous slide. So now what I want to do is I'm going to do a from here. Okay, what I want to do now is I'm going to want to solve this differential equation. I actually want to find the population model. And what am I going to do? So I want to find that. I want to find P of t. And P of t, if you notice, has three different constants on it. It has this constant m. I'm going to need to find that. I don't know why it's not going yellow. I need to find m. I need to find k. And I need to find a. Those are the three things that I need to find. M, let's do those in green. I need to find M, K, and A. And if I find those, then I found all I need to do is put them together to construct the population model. Okay, and what am I going to do? I'm going to simply know from my notes that if I have this right here, if this is my equation, okay, I can go right to this by just picking out some things. Okay, and I'm going to have to use, don't forget, I'm going to have to use this initial condition. I will use it at the very end. So if I look at my model here right away, if I look at my differential equation, I'm looking at this guy right here. Oh yeah, I automatically am given M, which is going to be 1200. I'm automatically given K, because this is K right here. I'm automatically given K, so let's write that down there. K is going to be 0.0002, and then really all I need to do then is find A, because I know what M times K is. So let's go down here a little bit and have this. I know that K is this, already stated. I have 1200. Hey, what is MK? MK is 0.24, so now I have MK there. Okay, no pun intended. So I'm going to put in what I know in my model. All right, so I know M is 1200, bam. I know MK is 0.24, so I'm almost done. Almost have this without doing any heavy analytical work. If I know these two things, if I know this statement right here, and I have my notes, I know this, then if I'm giving the population model, I can come up with a differential equation. If I'm given the differential equation in terms of the population, I can come up with the population model that's in terms of t. That's the part that's confusing a lot of people, is that the differential equation is a function of the population, not a function of t. Okay. And if I want to find the population as a function of t, this is what I'm doing currently. Okay. So now all I need to do is find A. And what am I going to do to find A? Yeah, I'm going to use this initial condition right here, that P of 0 is 20. So I'm going to put 0 in for T. What does this tell me? T is equal to 0. When T is equal to 0, the population is equal to 20. It's right here. Okay. So what am I going to do? I'm going to put 20 in for P of T right here. Put 20 in here. I'm going to put 0 in for T right there. And what does that give me? Oopsie. Let me move this guy up here out of the way. He gets in the way a lot. Okay. All right. So what does that tell me right here? It tells me true or false, 0.24 times 0 is 0, negative 0 is 0, e to the 0 is 1, so 20 is equal to 1200 over 1 plus a. All I'm going to do now is solve for a. Multiply both sides by 1 plus a. Did it? 20 plus 20a is 1200. 20a is 1180. Divide by 20. 1180 minus divided by 20 is 59. So now I have all the pieces. I have my m, I have my k, I have my a. So here's the solution. Here's my model. And if I go to my graphing calculator, well, I don't have my graphing calculator pulled up, so I'm going to wait. But this is a very short video. All right. So what do we do with this video? We looked at the growth model by given the differential equation. And then by using, which was easy, just pick out the maximum carrying capacity. Half of that, the inflection point is going to be at 600. And the only thing I need here is this point right here, which is 0.20. Point here is 0.20 on my population. And then the other thing I did in this video is I actually solved the differential equation. I actually found the growth model. I found this dude right here by these two statements here. That if I'm getting, these are if and only if statements, by the way, they go either way. If I'm given that, I can go here. If I'm given here, I can go here. Okay? And then that model came out to be that guy right there. So I'm going to end this video. Take a little picture here. What's up? All right. I will see you soon. We're going to pause this video. Hopefully you can sketch some logistic growth models by looking at their differential equation. Good day.